units account for about 49 gigawatts. In terms of capacity installation, it's only 2.4% of the total installed capacity, actually. In terms of the annual power generation, the nuclear power generation accounts for about less than 5%, 2.9% of the total generated electricity, which is about 350 terawatt hours. At the moment, there are 11 nuclear power plants units which are under construction, the total capacity of which is about 12 gigawatts. Of this capacity is also within this capacity is also the 200 megawatt of the gas-cooled reactor, the demonstration plant, which we will talk about later on. Now, for the role and for the future of nuclear power plants on mainland China. The first aspect is to meet the energy demand increase or the power demand increase now, currently, and in the future. You know, in the past 20 years, the electricity demand has grown up, has increased significantly. And in the future, we expect not that strong growth, but still the power demand will still increase. Second aspect is for structure optimization, by which I mean to optimize the energy supply structure or the electricity supply structure. Later on, I will explain this with one slide. The third is to ensure the energy security. You know, China imports a lot of energy from overseas, from other countries, mostly oil. Last but not least, nuclear technology, nuclear power technology is seen as a high-end technology. So the country's policy is to support the advancement of these kind of high-end technologies. So what would the future be looking like? We have now about 50 gigawatts, and we expect that 15 years from now, in 2035, the installed capacity could reach something like 150 gigawatts. And generated power could account for 13 to 14% of the overall power generation. This could be somewhat optimistic. I personally would expect that in 15 years from now, the installed capacity could exceed 100 gigawatts. That roughly means big reactors, about 100 big reactors of 1 gigawatt power level. So that means China would be probably the country with the largest nuclear power installation, nuclear power generation capacity. Next slide, please. This is a picture showing where all the nuclear power units under operation and construction are located. In one word, they are all located on the coast. They have coastal size in the coastal provinces. So far, there have been no nuclear units inland. Okay, thank you for this slide. Next slide, please. I see some comments popping up. Maybe we could discuss later on. I talked earlier, a few minutes earlier, about structure optimization, and this picture is what I mean by structure optimization. You see, in China on the mainland, we have about 60% installed capacity from coal, but 18% from hydro, less than 3% from nuclear, and 10 from wind and 10% from solar. That in terms of capacity. But in terms of generated generated power, generated electricity, more than 70% is from fossil, from coal, and 16% from hydro, less than 5% from nuclear. Wind and solar together are about 7%. So you see, the greater part of power is still generated by coal, and that causes the problem of concern in terms of pollution and carbon dioxide emission. So in particular, from this context, we need more nuclear power now and in the future. Next slide, please. Next slide, please. Yeah. China is now doing a lot of development of advanced nuclear reactor technologies, including large pressurized water-cooled reactor technology, the high-temperature gas-cooled reactor technology, sodium-cooled fast reactor technology, and other advanced reactor concepts, including small and modular reactors of water-cooled reactor type. We are building a modular gas-cooled reactor plant, and we are also building a fast-cooled reactor demonstration plant. So overall, China is investing a lot on advanced reactor development. Next slide, please. So let me come to the real topic on gas-cooled reactor. Since I'm speaking to a great audience today, some basic things about that technology. Probably most of the audience are familiar with light water reactor technology, which consists basically uranium dioxide fuel, metallic cladding, light water as coolant, light water as moderator, and metallic materials as core structures and pressure vessel. So this is a system, this is a nuclear reactor system, which finally dictates its characteristics or technical features. Whereas on the other end, the high temperature gas-cooled reactor use the same fuel, uranium dioxide, as fuel, but has ceramic coatings as cladding, and helium as coolant, graphite as moderator.
Excuse me, Professor Xinyu Liang, your voice is not clear. Sorry.
Is it now better?
Yes, better, right.
Okay.
Yeah.
Helium as coolant, graphite as moderator, and graphite also at the same time as core structure materials. So this is the system composition of the high temperature gas-cooled reactor. And this system composition dictates its features of that reactor type. And these features include, first, the system is high temperature resistant, meaning it can provide high temperature heat up to 700 to 900 degrees centigrade. Second, the basic physical feature is the reactor is less compact because it uses graphite as the reactor moderator and structural materials. Inherently or physically, the reactor core is larger. Okay, next slide, please. The reactor core is larger and less compact, and the transients will run slowly. This is how the gas-cooled reactor or the high-temperature gas-cooled reactor fuel looks like. You see the right ball is the uranium kernel, we call it the uranium kernel, and then it is coated by several layers of ceramic carbon material, forming the coated particles. And tens of thousands of these particles would be dispersed, would be put into a graphite ball to form the fuel element of this reactor type, which is completely different in comparison to the light water reactor fuel rod fuel type. These are completely two different reactor fuel element types, and this is really the fundamental difference of the two reactors, of the reactor fuel technology, reactor core technology. This next slide, please. This is where the high temperature resistant features comes from, this reactor type. So although many people, including me, call modular high temperature gas cooled reactor is the fourth generation reactor type, but actually it is not a new concept. It started from 1950s, 60s. In 1960s, 3 test reactors were built in Germany, in the United States, in Great Britain, respectively. And in the 1970s to 1980s, 2 power plants were built, respectively, in Germany and in the United States. Unfortunately, roughly up to the end of 1980s, all those reactors came to shutdown conditions. Some of them are already decommissioned now. After that, let's call first generation or second generation high temperature gas cooled reactors. In fact, it is after the 3 Mile Island in 1979, the modular concept of high temperature gas cooled reactor was proposed and followed in Germany, in the United States, in China, Japan, South Africa. Among these countries who follow this reactor type, China and Japan built 2 test reactors. And based on these test reactors, China is building the industrial demonstration plant, and internationally, the international community is following the Generation IV research and development program. China and Indonesia are both members of the Generation IV forum pursuing this technology. Next slide, please. Can I have the next slide? Yeah, the modular high temperature gas cooled reactor are characterized by, actually already, I'm sorry, can you come back to the last slide? Can you go back to the last slide? Can you hear me? Excuse me, can you hear me? Would you please go back to the last slide? Can you hear me? I could hear no response. Last slide, please. Go back, please.
Okay.
Go back. Go back. Go back. Please go back to the, yeah, yes. Thank you. Oh, no. Go ahead. Go. That's too much back.
Oh, which one?
No. Go ahead, not go back.
Oh, okay.
Go further. Continue. No, go back. Can you go back, please? Go back. Go back. Yeah, stop. Next. Yeah, stop. Stop here. The modular HTGR concept has two basic features. First is its safety. In terms of safety, I can only mention that it has good self-reactor shutdown feature. It has excellent decay heat removal feature, and has good radioactivity containment feature. As a result of all of these, it meets the safety goal that no offsite nuclear emergency response is necessary, is required. So this is a basic requirement of the Generation IV nuclear systems. So we can say in this context that modular HTGR is a Generation IV reactor technology. The other feature I have already mentioned is its high temperature feature. It can reach 700 to 950 degrees centigrade, which is suitable for both high efficiency power generation and for various applications of process heat. Okay, thank you. Next slide, please. Well, China started the development of this type of reactor technology actually as early as in the 1970s. We started with the research and development of key technologies, including fuel development, reactor design methodologies. In the 1980s, the central government of China decided to build a test reactor. And we started, and in 2000, in the year 2000, the test reactor was erected, was constructed. And after that, we started an industrial demonstration plant project. And that is the so-called HTRPM project, the construction of which started in 2012. Now it's under construction, or more specifically, more accurately, it's under commissioning now. We hope that after commissioning, it will, after it's put into full operation, we'll continue with this roadmap. We'll continue with this development approach, coming to more commercial projects. Thank you. Next slide. Yeah, a few slides about the test reactor. The test reactor was approved in 1986. The construction started in 1992. No, the construction was approved in 1992. The construction started in 1995, and it took us 5 years to finish that construction. And in 2003, it went into full power operation. Some of you have visited us to this test reactor site. Next slide, please. Yeah, this is a cartoon-like picture of the test reactor. We have on the left side the reactor part, on the right side the steam generator part. The reactor has a total thermal power of 10 megawatt, and the heat generated by the reactor steam generator is given to a steam turbine system which can generate 2.5 megawatt electricity. The helium works under a temperature from 250 to 700 degrees centigrade. You have you can see some of the pictures of that test reactor, the fuel, the reactor core, and the control room. Next slide, please. The test reactor has been utilized for a number of purposes. One of the main purposes is to do safety testing. We have done a series of safety experiments to demonstrate the safety features of this reactor type, including, for example, during the normal operation of the reactor, we suddenly shut down the primary cooling, or during normal operation, we even withdraw some of the control rods. These are really very serious scenarios within the nuclear power plant. So through these experiments, we demonstrated the safety, let's say, the safety features of this reactor type. One time, we have invited something like 40 international experts coming to us and witnessed some of these safety testing. Next slide, please. Although this test reactor is very small, the purpose of this test reactor is not at all to generate power to the grid, to supply power. But it has helped us a lot, has accomplished some very important achievement in terms of technology, in terms of plant technology, system technology, field technology, in terms of collecting, gathering license experience, most importantly, in terms of capacity building. Through this small reactor, we have built the capacities of research, development, design, engineering, component manufacturing, commissioning, and operation. So with a reasonable cost. So I see these as the important roles of a test reactor. Next slide, please. So after the test reactor, it is obviously very logic to have the next step. The next step would be to build a larger plant for industrial application. In 2006, we get the project approved by the government as a national key project to build a 200 megawatt plant on a coastal site in China. Next slide, please. This industrial project, this plant is called HTR-PM, meaning high temperature reactor pebble bed module. The project consists of 2 reactors and 2 steam generators, meaning 2 nuclear steam supply modules. The 2 modules are connected to a steam turbine system having an electrical power output of 211 or 210 megawatt. Each reactor has a thermal power of 250, so 2 reactors make 500 megawatt together. The core is about 11 meters high and 3 meters in diameter. Helium works under 7 megapascal, being heated from 250 to 750 degrees. The fuel has an enrichment of 8.5%. The steam turbine is somewhat a standard industrial turbine. This steam generated is at 566 degrees at 13.2 megapascal. Let's say that's a conventional turbine. The 2 reactors are in the same building, in the same reactor building. You see on the right lower end the picture of the reactor building and how these 2 reactor steam generator modules are housed in the reactor building. Next slide, please. Yeah, next slide. Because it is the first big modular plant, we have to do a lot of verifications of the design, of the system design. We have built a big laboratory. We have built a 10 megawatt helium testing loop working at in full scale in terms of pressure and temperature. And we have done the design verification tests for the various systems and the components used in the real demonstration plant. Next slide, please. Now about the equipment or component manufacturing. It is the first kind of such a plant, but the Chinese manufacturer, the Chinese nuclear industry has got a lot of capacities from the other nuclear power plants project. So in the end, we are able to have our equipment system manufactured mostly in China, except the graphite blocks. Graphite blocks are imported from Japan. All other key components like fuel, pressure vessels, steam generators, helium blowers are all manufactured by Chinese industry, by Chinese companies. Next slide, please. Some of the pictures taken during the equipment manufacturing. This is the reactor pressure vessel. It is manufactured in Shanghai. Next slide, please. The civil construction work. The first concrete was put in December 8 years ago in 2012 after the Fukushima accident. It was originally planned earlier for the first concrete. There was some delay because of the Fukushima accident. Next slide, please. Yeah, here are some pictures showing the progress of the construction work on the construction site. It's a lot of work. I should tell you that I worked on the slide for several years with the company, and it was an interesting experience. I'm not sure if I think Professor Jarrod visited there. Some of our Indonesian friends, colleagues visited the site last year or the year before. I think last year. Yeah, it is a coastal site in Shandong province, a very beautiful site, and I would like to extend an invitation to all of you. If you get the opportunity, you are welcome to visit that site, to visit our reactor plant. Next slide, please. Yeah, these show some of the installation processes at the construction site. This is the, let me see, the left picture shows the installation of reactor internals, the upper parts of the reactor core. Okay, next slide, please. Here are the milestones of the construction work. I don't want to go through them. I already mentioned that it started in 2012, at the end of 2012, and the construction work was basically finished this year, in the middle of this year. Construction meaning the construction of the civil constructors and the installation of all the systems and components. Last month, it was officially announced that the project has started its commissioning work. In China, the other big light water reactor projects, the construction work usually takes 6 years, sometimes less, sometimes more, for those proven units, for those proven technologies. With us, it has taken longer. There were a number of reasons. One of the reasons is the delay of equipment manufacturing, because this is, for some cases, the first time for the companies to manufacture such components, and because some of the components have new designs, have its first kind of designs, so it has taken more time than planned, than expected. But fortunately, we have started the commissioning work about 1 month ago. For the proven technology units, commissioning work usually takes a few months. But we don't know how exactly long it will take us to get the commissioning work finished. But I personally hope, we hope, we can finish the commissioning work within next year, and we could possibly start the operation next year. When exactly, I can't tell. Next slide, please. Yeah, about next steps. I mentioned that after this demonstration plant, we would like to go more commercial, for more commercial application, for power generation and for cogeneration, supplying power and process heat simultaneously. And our industries, our nuclear industries, are cooperating with us to work on this intensively. They were also doing a lot of research and development for hydrogen production using heat from high temperature reactors. This is also a big R&D project. Next slide, please. Yeah, to conclude, I would like to say that the high temperature gas-cooled reactor, or more specifically, the modular high temperature gas-cooled reactor, is an important component of advanced nuclear power technology development in China. It has drawn, let's say, a great deal of attention from both the government and nuclear industries, and from the potential users, from the potential market. This kind of technology is suitable for high efficiency power generation and for various heat applications. Now, looking back to the gas-cooled technology development in China, as I already mentioned, we started with key technology development, reactor and system design, fuel technology development, capacity building of human resources, and so on. And after that, a key step is to design, to build, and to operate a test reactor. And after that is a demonstration plant, which we are now, which is the focus of our current effort. And after that, we hope to go more commercial. This next slide, please. I think this should be the last slide. Thank you for your attention very much, for your interests. Before I close, I would like to mention 2 facts that has drawn attention from mine. The first fact is on Monday of this week, that means 4 days ago, the 2 presidents of our to country had a long phone call and pay special attention to the news report, which is encouraging for me very much, because as many of you know, we have close ties in this high temperature gas-cooled reactor area, and I hope the good relations between the two governments would further promote, would further facilitate and support our cooperations in this high temperature gas-cooled reactor area. The second fact is that yesterday the Chinese central government has approved. The central Chinese government has approved further four big light water reactor power plants units to be started. So we will. That means we will continue to see nuclear power plants constructions in China. So with this, I would like to thank you again for your kind attention, and I would be happy to respond to some of your questions.
Thank you very much, Professor Yu Liang. So I would like to invite several persons here to give comment or question. First, I would like to invite Dr. Asnasio Lasman, the former chairman of Bapeten. Please, Pak Asnasio, you can ask your colleague from Germany, the alumni of German. Okay.
Thank you, Pak Jarod. Yeah, thanks for your nice and clear presentation, Prof. Yu Liang Sun, and my congratulations of your successfully big job to realize not only 10 megawatt thermal HTR, but also the HTR PM 200 megawatt electric, and so far is last month, yeah, was commissioned. I believe that there were a lot of discussion, a lot of coordination to bring the DID, the detailed engineering design, from your side to the industries to realize the project. And it was done successfully. Once again, my compliment. About the HTGR technology from the safety point of view, of course, don't need to be discussed again, because in the extreme situation, that is, there is no cooling in the reactor, and also in the same times, all of the control elements are failed, the HTR is still safe. So this is shown not only from the theoretical aspect, but also by conducting direct experiment with the HTR. Another advantage of HTR is the high temperature will be produced up to 750 grades Celsius. It means more than 400 grades Celsius above the outlet temperature of light water reactor. Therefore, the HTR PM could be used also as cogeneration reactor, as you see for the hydrogen production. But could you explain what is the HTR PM program for cogeneration except for hydrogen production? Secondly, the last question of mine is about the human resource development. It's very, very important in any country. How many universities in your country have nuclear reactor technology development department, and in total, how many students are studying in that field? Also, thank you very much, Prof. Yu Liang Sun.
Please, Professor Yu Liang.
Thank you, Dr. Lasman. If I understand, the first question is about cogeneration. For the current project of HTR PM, it is just for power generation.
Okay.
And from this design of 200 megawatts, we would like to go to something like 600 megawatts for power generation. Yeah. And in terms of cogeneration, we really have to study, to investigate about the market demand, about the user requirement, how much electricity, how much heat is needed for a specific site, for a specific application. We are now working with the petrochemical industries, for example, to see if a modular high temperature gas cooled reactor could match some of their potential demand. So this is really a good question. Because if we talk about electricity, when we talk about electricity, we are the producer, and the buyer is the grid, the electrical grid. So the size, the power size, is probably more our choice. But if we think about process heat applications, the size really has to meet the requirement from the potential users. So we have to do more market studies. Your second question is about human resource development. And you ask about some specific numbers. I used to know these specific numbers, but I don't have them clearly in mind now. I think in China overall, there are dozens of universities or educational institutions which have education programs of nuclear engineering. Something like 30 or 40, something like 40, I remember. Like 10 years ago, there is a boom of nuclear industry, of nuclear engineering. So some more universities started nuclear education programs. Not only universities, in China there is a Chinese Academy of Science. So there are also a number of institutions under the Chinese Academy of Science system, which offer nuclear education programs. In terms of number of how many students study nuclear engineering each year, I can hardly give exact numbers, but I don't remember. I can hardly give. But as far as I know, my university, for example, enroll each year, let me see, about 200 postgraduate students, and also I think less than 100 undergraduate students. I know two big universities, they have much larger undergraduate programs. They enroll each year 300 to 400 nuclear engineering students. Each year, I would expect something like 200 graduates. Well, I have to check with this number. But the facet is I think there is a good balance between the demand and supply. I mean, our graduates could all find relatively good jobs in the nuclear sector. And I think the nuclear sector is also very satisfied with the quality of the graduates. Thank you.
Thank you. Great.
Thank you very much. The second person I would like to invite is Professor Zaki Suud. Please, Professor Zaki Suud, if you have any questions.
Thank you very much, Professor Jarot. Thank you very much, Professor Sun Yuliang, for your very nice presentation. I have some questions. First, you mentioned that you have strong nuclear power plant program in China, especially in 2035. And we see that if in 2040 or 2050, you will have so many number of the nuclear power plant. my question is, do you have some description how many % of this nuclear power plant will be high temperature gas-cooled reactor at that year, around 2040 or 2050? This is the first question. The second question, you use here the steam turbine cycle. Do you have some planning to use gas turbine cycle? And the third question, do you have some planning to test the core pressurized accident in full scale for HTRPM? Okay, thank you very much.
Okay, thank you for your questions. I hope I've understood all of your questions. The first question is, what is the future of modular high temperature reactor in, let's say, 20, 30 years from now? Well, I can't give specific numbers in terms of how many units or what would be the percentage of high temperature reactors. In 20 or 30 years from now, I am pretty sure that China would be the country with the largest number of nuclear power plants. It's very much dependent on how much we will find, where we would find the process heat applications for the gas-cooled reactor technology, and how we could potentially develop nuclear power plant sites inland, not coastal sites. I think the advantage of HTGR or modular HTGR is its high temperature potential. And if we could succeed in bringing this reactor technology in the process heat application, there could be a very reasonably large market for this reactor technology. If we could not succeed in this direction, if there is only a marketplace for power generation, and then the role of this technology could be somewhat limited, because the large light water reactors have already taken the major marketplace. So what I would say is, it's really up to our future effort, up to the future development of the market situations. But anyway, we would like to see, or I would like to see, or I can make projections that a number of modular reactor units could be projected in the next couple of years. Your second question is regarding steam turbine or gas turbine. I think for the next foreseeable future, for the next 10 or 20 years, the major option would be still steam turbine, because to some extent the technology would become, or is becoming, mature, is becoming available. Gas turbine requires still considerable amount of development work, of testing work on the turbine part, on some of the safety aspects. So far, we have some limited research and development work on helium turbine, but not on a high profile. I don't know how much work is being done in Japan within JERI. So I would also be interested to see how long it will take for the gas turbine to come. Of course, helium turbine directly being coupled with the reactor is a much more simpler version of this technology, offers a lot of advantages, but it's a question of technology challenges and timing. Your third question is about safety testing. What is exactly the scenario you mentioned? Loss of coolant accident?
The pressurized accident.
You mean depressurization or?
Yeah, the pressurized.
Okay. I wouldn't expect that we would conduct such a scenario testing, depressurization. We could do some simulations, probably. But so far we have not decided. There have been some proposals to conduct such kind of simulations, such kind of testing with the real plant, but we have not come to the decision to do this. Thank you.
Okay, thank you very much.
Thank you, Professor Gisud. And then the next person is, I will invite Dr. Fiber from Sriwijaya University, South Sumatra. Please, Dr. Fiber. Silakan, Pak.
Sun Yuliang, your presentation is exciting. In this session, I have 3 questions. The first question, in the high temperature gas cooled reactor bubble bed module or HTRPM, how the tricycle fuel arrange in the mass? And what reason to choose the one? The second question is, in your HTRPM design, you use uranium oxide as fuel. Fuel enrichment is 8.5%. I want to know how long to fuel refueling or fuel supplying in the reactor core. And the last question, how do you manage the spent fuel of the HTRPM design? How does the reactor burn its spent?
Maybe there is a problem with the internet, Pak Fiber.
Yeah, I'm very sorry. I know you have 3 questions, almost all related to fuel, but the voice quality, the voice transmission quality is not so good. Probably Professor Jarrod, you can
Okay.
explain.
Maybe Pak Fiber, you can please say it again, because we cannot hear clearly your questions.
Okay, may I write my question?
Okay.
Okay.
Okay, through chat, please.
Okay.
Yeah. Okay. There is, well, while waiting for the Dr. Fiber to write down his question, there are many questions from the audience. One of the questions from Miss Gloria. Her question is, does this reactor use helium gas as a coolant? How to prevent and control the potential risk of explosion and fire from helium gas, considering, well, it's lost. Considering that what this reactor uses is helium gas, why you choose helium gas? This is the question from Miss Gloria, please, Professor Yulia.
Yes, thank you for the question. Yes, you are right. Helium is chosen as to serve as the reactor coolant because it is chemically inert. So it has good properties in terms of corrosion. It has in terms of chemistry, and it also has good properties in terms of physics. It does not eat too many neutrons, let's say. So it's a very good reactor coolant. And because it is chemically inert, so we have very, very less concern of fire of the graphite in the reactor core. I hope this addresses the question.
Okay, yeah. I think the question from Dr. Fiber, there are three questions. The first one, in high temperature gas-cooled reactor pebble bed module, HTRPM, how the threshold fuel arranged in pebble bed? Randomized, square, or hexagonal lattice? And what the reason to choose the one? That is the first question.
Okay.
Yeah, please.
Okay, let me first address the first question. The threshold coated particles are randomly dispersed in the graphite matrix. So that is the way the fuel elements are produced. Okay, and secondly, the pebbles, the fuel spheres or the fuel pebbles are also randomly loaded into the reactor core. So in both ways, from both aspects, the way is random statistically. Yeah.
And this,
yeah.
Can I continue the second question?
Yeah, please.
Yeah. In your HTRPM design, you used UO2 as fuel, with the fuel enrichment is 8.5%. I want to know how long to fuel refueling or fuel shuffling in the reactor core.
Okay. Yeah. Let me continue. I just remember I didn't finish. I didn't touch every part of your question. I think one part of your question is the choice between prismatic and pebble bed. Well, I think both options have their advantages and disadvantages. The reason why we chose pebble bed fuel is we just simply started with that. So I don't think there is a strong technical argument to choose pebble over prismatic or to choose prismatic over pebble fuel. We just started with that, and we got more experiences with this option, so we continued with the pebble option. Your second question is about the shuffling time. Let me consider how to address your question. I don't have my colleagues here, and I don't have the specific number in my mind. It is a challenging task. Every day, every hour, every minute, we have to shuffle a big number of fuel elements. And within this shuffling, we have to measure the burn up of the fuels of each fuel. We have to check each fuel still is still after it comes out from the reactor core, whether it still meets the specifications, whether it is still perfect, whether it is still good to be sent back to the reactor core. But because I don't have the specific number in my mind, is an easy task to calculate. You see, each reactor has 250 megawatt power, and the burn up of the fuel is 100,000 megawatt day per ton uranium. So out of this number, we can very quickly calculate out how many balls are discharged from the reactor core every day, and how many new balls need to go into the reactor core. Sorry, unfortunately, I don't have the specific number, but it is a big number in terms of every minute or every hour.
Okay, and the third question, how do you manage the spent fuel of the HTRPM design? How does the reactor burn his spent fuel itself?
Sorry, can you please say it again? How do we manage?
How do you manage the spent fuel of the STRPM design? And how does the reactor burn his spent fuel itself?
How does the reactor burn the spent fuel itself?
Yeah, I think Pak Fiber, could you explain your questions about to burn the spent fuel itself? Hello, Dr. Fiber, can you unmute your microphone?
Well, for the first part of the question,
yeah,
the spent fuels, the spent pebbles, after they have reached their end discharging burn-up, they will be put into casks. And all the spent fuel will be spent on site inside the reactor building underground. That is so far the option we have chosen, because this is the first plant, this is the first facility, and we haven't closed the we haven't had an established fuel cycle facilities. So the spent fuel are foreseen to be stored on site in the reactor building.
Okay.
The second part, I need clarifications.
Okay, Pak Fiber, could you explain what is the I don't know, what do you say about the spent fuel itself? Can you unmute your microphone? Oh, okay, I will continue with several questions. There is question from the YouTube. One question from YouTube is the STRPM began to commission in July, as you gave the presentation previously. Well, you have already explained it is very difficult to estimate when in the next year to operate. But his question is, what is your estimation that STRPM will in full operation or connected to the grid?
Okay. To give a simple answer, I hope commissioning work could be finished before the end of next year.
Before the end of next year.
Before the end of next year.
Okay. And there is one question, it's very interesting. You mentioned in the last of your speak about the joint communication between the President Xi Jinping and President Joko Widodo of Indonesia. Is there any specific issues on the nuclear power, or maybe HTGR? One question in the chat, I think, asked you, well, very broad and very political question, I think.
Yeah. I did pay attention to the news report. On our side, I think President Xi Jinping is a graduate from our university.
From Tsinghua, yeah.
From Tsinghua University, and he knows what we are doing.
Okay.
He knows the gas-cooled reactor technology. He used to be the governor of one provinces in China. And at that time, he even had some technical interest in this technology. And in their telephone conversations with of the two presidents, I think they mentioned scientific, technical areas. They mentioned President Xi mentioned specifically the initiative of your president. I don't remember the English name. It's you have a big framework, like ocean. Your country or your president has a big framework.
Oh, Ocean Toll or something like that.
Yeah, it's something like that.
Toll, yeah.
Yeah. The two presidents supported the cooperation within these frameworks. Yeah. I could also report that since since almost 3 years, my institute and Batam are running a joint laboratory on high temperature gas cooled reactor technology. We have done a lot of trainings, a lot of joint effort on reactor codes application, on reactor design, on nuclear, on gas cooled reactor simulation. And we have also learned a lot about the nuclear infrastructures, capacities in Indonesia. And we are approaching the end of the first phase of this joint laboratory program. And we are going to start the second phase of this joint lab program. The Chinese government fully support this collaborative effort, and we would like to continue. We would like to see more results from this cooperation.
Okay. Well, I have two questions. First is the status of STR-10. You have earlier, before the STR-PM, you have already operated the STR-10 in Tsinghua University. What is the status right now? Is still in operation, or after finishing the commission of the STR-PM, you will close the STR-10? And the second thing, when I went in China several years ago, you have a big timeline or roadmap to build another or bigger STR 600 megawatt. What is the progress right now?
Yeah. Thank you, Dr. Jarrod. On the HTR-10, on the test reactor, it is still in operation. Or to be more exactly, it is always in operable status.
Okay.
But because it is not a commercial unit, it is just an experimental reactor. As every experimental reactor everywhere in the world, it is not continuously operated. Maybe each year it is operated only for some months or some weeks for specific purposes. In this context, the HTR-10 reactor is still in operation. And it will also not be closed after the operation of the HTR-PM is put into operation. The test reactor HTR-10 maintains its roles as a test reactor, doing experiments, human resource for training, for various kinds of activities. Okay, that's your question about HTR-10. Your second aspect is about the 600 megawatt. Yeah. I shortly touched on this in my talk. I mentioned our current focus is the commissioning work of the demonstration plant. But we are working mainly on two streams. The first stream is the modular HTR for power generation. And on this stream, we are going to 600 from 200. So each reactor building will consist of 6 reactor modules. But your question is about the progress. What is the status of this initiative? We are working on sites of this 600 megawatt. The sites have not been decided yet, but we are working very actively on it.
Okay. There is one question from a woman, I think Miss Hasriati Saptawati. She asked, I want to read her question. First, Dr. Sun Yuliang said that the constructing of the reactor is one of the main focus of the government program regarding nuclear fuels. I wonder how much help that the government gives to help the construction progress. And one more question is, the government or public has ever questioned the idea of constructing the nuclear power plant? I think the two questions. First is how is the role of the government on the nuclear energy program, and the second is the public. Whether is there any questions or maybe about the safety or maybe about the anti-nuclear movement, maybe. I don't know.
Yeah.
Please.
Yeah. Thank you for your question and interest, as you said, from a lady. I remember another question was also from a lady. So it's a really pleasant experience that so many ladies in Indonesia are engaged in the nuclear things. The first question is the second question is about public acceptance. The first question, just try to remind me. The first question is
the role of the government.
The role of the government in that project.
Yeah.
I see two main roles of the government in that project. The first role is the political role. The central government of China takes a very positive, supportive policy toward the development of advanced reactor, and in particular to the high temperature gas cooled reactor. And this political support is, let's say, is a kind of guarantee to make this happen, and to probably to make this succeed. So the political support is mostly important. The second role is some financial support is put into the project. Some part of the money comes from the government, and the other part of the money comes from industry. And the governmental part of financial support, of funding support, is more for people like us, working in the university, and is for the research and development. A little bit noisy outside. I show some experiments, big experimental loops, big laboratories. All these kind of R&D work are supported by the central government. And some money is also given to the Chinese manufacturers, because for the manufacturers, they also need to do some, let's say, some new work, some development work. And for this development work, the money also comes from the government. And the government also put some money in the construction of that project. So in one word, the second major role of the central government is to provide money. So once again, the first role is to provide political support. The second role is to provide funding. Okay. Second question is about public acceptance. Public acceptance is an ever-growing issue in China. There are more people who get concerned about nuclear projects, whatever it is, nuclear power plants or fuel cycle facilities, or whatever nuclear is concerned. Some people have more concerns, and we can also understand this trend when people become more, let's say, more comfortable with their life. They don't care where this comfortable life comes from. The nuclear projects actually offered a lot of opportunities for the local people. So very quite often the noises or the opposing voices do not come from the local residents, do not from the local people, more from some let's say prominent figures, from some people who are very much against nuclear, or very much cautious. I shouldn't say very much against. They are very much cautious about nuclear, and they make many voices on the internet, in the media, and so on. So we have it's becoming an issue, and we have to deal with this. Within every big nuclear project, nuclear power plants or other projects, we have to go through a process to inform and interact with the local public. This is a legitimate requirement on nuclear projects. So far, it has not been challenging, not been that difficult, to get along with these public acceptance issues.
Okay, well, I think it's very interesting for Indonesian to ask you about the Chinese condition when we talk about the public acceptance. And one more question from YouTube. There is one very interesting. Usually Indonesian will ask about the economic matters. How is the cost for the STR-PM? The cost to construct that STR-PM and the price of the electricity.
Yeah. Well, I know I expected this question. I know it is the most difficult question to tackle. High temperature reactors, traditionally or historically, are more expensive than light water reactors. In 1970s, 1980s, there were a number of orders for large high temperature reactor plants. But because of the 3 Mile Island, and probably also because of other economic or commercial situations, all the orders were canceled. And now we start to develop modular reactors, small reactors. As I said at the beginning, small reactors normally, usually, or inherently are more costly than bigger reactors in specific sense. This is also our project experienced. This is the first project, the first plant. The power is small. Both the direct costs and the indirect costs, the specific costs are higher than those big power plants. At the moment, the big light water reactors, the construction costs is about $2,500 US per kilowatt installed power. And the electricity, the cost, the power price, the busbar price of electricity to the grid is a result of discussion or negotiation between the producer, the grid operator, and the central government. At the moment, the nuclear electricity price is comparable, is at the same level to the fossil-fired plants, to the coal-fired plants. It's generally for nuclear, it is a challenging issue because the nuclear facilities are designed more and more robustly. We need to have more and more systems, equipments to make it more safer. So it's becoming more and more costly. While on the other side, other options of power generation like solar and winds, they are becoming less and less costly. To address your question on gas-cooled reactor, on the modular gas-cooled reactor, we have done studies. If we start from the current demonstration plant, going to a mass production, let's say, if we have 10 units or 20 units and 30 units, eventually the power price will go closer and closer to the light water reactors. The electricity price could go to the level of something like 6 to 7 US cents per kilowatt hour for a target plant.
Okay. Okay. One question from Topan. You know Topan, I think. Dr. Topan Setiadiburan. He asked.
Where is Topan?
Maybe Topan, you can ask Dr. Sun Liang directly. Pak Topan, please. Where is Pak Topan? Oh, he's already left, I think.
Yeah, where is he? He's hiding somewhere.
Yeah. He has one question. The STRPM total power is 210 megawatt electric from 2 reactors. If only one reactor in operation, is the turbine able to follow this load reduction and can produce around 105 megawatt electric?
The simple answer is yes. Maybe the output wouldn't be just exactly 50%, but the turbine can operate on 50% power level.
Okay. Pak Topan, please, if you have any question.
Yeah, thank you. So that's it's good news. Thank you. So we have, as you explained, we have 2 reactor and 1 turbine. So the common question would be, what would be the problem is if one of the reactor is off. So it's if it is okay, then it's good good news. But more radical maybe, is it possible to build HTRPM with its license, but only one reactor, single reactor? So because we only need 100 megawatt electric, for instance.
So what was your question regarding license?
So I mean, is it possible to use the same license of 200 megawatt electric HTRPM, but we only build single core first, so not directly double core, twin core.
Do you mean for a new project with only one reactor?
Yes.
I don't know what the situation otherwise in other places outside China. Well, I think the logic or the principle in China is, for every nuclear project, you need a license. Independent whether it is a new reactor, it is an old reactor, it is a proven reactor or not. It is a project specific. For every project, you need a license.
Oh, I see. You mean the design license, or?
No, the license is there is no design license in China. There is only a construction license and an operation license.
Oh, I see.
There is no design license.
I see. Thank you.
Okay. There is one question from the YouTube about the site. Professor Sun Liang, can you tell us about selective location of those 200 megawatt pilot plant SGR-PM is made in terms of geographically and demographically? Is that located in remote island and rare population? The location.
I didn't quite get the question. It's about siting.
Yes, siting is that the location for that STRPM is remote area with the not dense population, far away from the town or the city's crowded population.
Yeah. I think this is generally speaking. This is also agreed by the Chinese regulatory body. Generally speaking, the modular high temperature gas cooled reactor has much easier requirement or much less requirement on siting. So it could be constructed close to residential areas. But of course, if the user is in a remote area, of course, there is no problem to build it in remote areas. So the answer is siting is more flexible for small reactors, for including the modular high temperature reactors. In China, big large reactors are not allowed to be built close to cities, close to residential areas, but small reactors are possible.
Okay, there is another question from the lady, Miss Gloria. Does China has uranium mining to produce the nuclear fuel? Do you have nuclear uranium mining in China?
Uranium mining, the question was. Oh, yes.
Okay.
China has uranium resources, uranium mine resources, and China has its own nuclear fuel industry, starting from mining to enrichment, to fuel elements production, spent fuel storage, and even reprocessing. So China has a whole nuclear fuel cycle industry, including mining. But China is not very rich in uranium resources.
Okay, thank you. This is last question from the audience, from the YouTube, maybe young generation. Not talking about HTGR, but talking about Tsinghua University. Is there any chance for the young generation, the Indonesian, to get the scholarship from Tsinghua University to study in your very famous university? If you have
to get scholarship, whether it is possible. Yeah, it is quite possible. In the past decades or past few years, we have had a policy which is very favorable to overseas students from outside China. Chinese government offers a lot of scholarships to foreign students, and in particular, the students from, let's say, from developing countries. So we have a big number of international students from Asia. Of course, also students from Europe, North America, and so on. We do have a good number of international students on our campus. It's a beautiful campus. I would like to welcome you to apply or to seek the application opportunities.
Okay, thank you very much, Professor Sun Yuliang. I think there are still many questions, but I think the time is already more than 5:30. Thank you again on behalf of Indonesian Nuclear Society. Thank you for your presentation. It's good for us. There are more than 300 audience from Zoom, and there are many people also using the YouTube. I think this presentation give Indonesian audience about the scope of your progress of your work on the HTGR, so help us to understand about everything about nuclear energy in China. As far as I know, the China have many programs, not only HTGR, also in PWR, also in molten salt reactor, also in Shanghai, for example.
Every possible.
Yeah, and also in renewable solar, wind, as you explained. But anyway, I want to hear next year the good news on the operation of HTRPM. This is good news also for the nuclear community in Indonesia. Again, thank you very much for your presentation. Hope we can meet you again in the near future. Thank you. Yeah, thank you.
Thank you very much from my side. Thank you for your interest, and my best wishes to all of you. Safe and everything goes well. Thank you.
Thank you.
Bye-bye.
Bye-bye, thank you. Terima kasih semuanya Bapak Ibu sekalian. Kita sudah mengadakan presentasi tentang small modular reactor. Nanti tanggal 17 kita mungkin akan mengundang dari pihak KERM Argentina untuk berbicara masalah KERM 25. Mereka juga menarik. Nanti juga kita akan mengundang teknologi-teknologi lain. Jadi HIMNI tidak akan membuat diskriminasi tentang teknologi apa saja, termasuk kalau nanti kita akan mengundang dari pihak yang penyuka thorium. Jadi ini menjadi suatu bagian dari HIMNI, asosiasi kita itu memberikan apa yang terbaik bagi masyarakat Indonesia. Sekali lagi terima kasih untuk Pak Asnasio, Pak Zaki Suud, Pak Fiber, Pak Topan, dan yang lain-lain. Sebenarnya tadi saya menunggu Profesor Ismail dari Kalbar, tapi beliau rupanya ada kuliah, memberi kuliah, jadi tidak sempat untuk memberikan tanggapannya. Sekali lagi terima kasih untuk semuanya. Thank you again, Professor Sun Yuliang. I think some of the audience from the China also watch this Zoom. Thank you. Terima
kasih.
Thank you,
Prof. Sun Yuliang. Thank you very much.
Thank you, Pak Jarot.
Terima kasih, Pak Susilo.
Terima kasih.
Ya, terima kasih Pak Jarot.
Terima Jarot.
Terima kasih Prof. Jarot.
Sami-sami. Moga-moga.
Saya mendengarkan sambil nyetir mobil.
Wah, hati-hati loh ini. Wah, ada Mas Wijanarko Hudi dari Kalbar ini juga kan ini.
Ya, ada itu Mas Wijanarko.
Ada Pak Basori dari UNAS, Pak Kiswanta, dan teman-teman Pak Hashim. Ada Bu Endiah, Pak Saiful Bahri. Tadi terima kasih ikut menjawab itu Pak Saiful. Ada Pak Yaryanto, pelukis.
Ya, makasih Pak. Makasih banyak Pak. Mantap Pak.
Pak reaktor kita itu Pak. Yaryanto itu.
Ada Pak Setio Pak. Pak Setio.
Ada Pak
Budi Setiawan.
Iya Pak Budi Setiawan. Saya sudah komunikasi dengan Argentina, jadi KERM akan bersedia untuk berbicara terkait progres mereka.
Terima kasih Pak Jarot.
Ya, sami-sami Pak Budi Setiawan. Wah, ini supporter PLTN itu.
Saya baru mendalami KERM nih, minggu depan insya Allah.
Oh,
hadir.
Ya, oke, moga-moga lancar semua. Ini memang perbedaan waktu 10 jam antara Buenos Aires sama Jakarta membuat saya harus mencari.
Iya, itu repotnya itu.
Jadi saya pilih pagi beliau, kita malam 7:30 gitu.
Nah, lihat Pak Saleh Kasim.
Oh, ada.
Apa kabar pasar minggu Pak Saleh?
Ini. Tadi ada juga dosen dari Pak Imam Sufaat nanya terkait suhu dan harga tadi ya, itu sudah jawab sama Pak Saiful Bahri. Ini.
Halo Pak Jarot, Prof. Dari UNAS Prof.
Wah, gimana Pak
Good presentation.
Terima kasih. Saya lama belum sempat ke sowan ke kampus UNAS ya. Ada Pak Salim Mustafa juga ini. Pak
Jarot, makasih.
Oh, sami-sami. Terima kasih.
Oh, Pak, itu Pak Project Manager.
Dari Voltek, Jakarta.
Oh, siap.
Pokoknya
sami-sami.
Kami dari rekayasa engineering Pak, terima kasih Pak.
Wah, ini rekayasa engineering ini.
Iya, rekayasa Pak kita.
Siap.
Support Pak, selalu hadir Pak.
Ya.
Tahu dapurnya tuh orangnya gitu.
Kangen Pak Topan, ketemu Pak Topan.
Ayo, kita desain lagi.
Iya, desain lagi Pak Topan nih.
Pokoknya kalau nanti HTRPM itu beroperasi, itu breakthrough itu.
Oh ya, luar biasa itu. Saya sangat menunggu Pak Jarot untuk. Saya selalu nanya Prof. Sun Yuliang, kapan itu beroperasi? Sehingga saya bisa nunjukkan nih loh, gitu. Kalau belum kan repot juga, gitu.
Ya, tapi itu tantangan kalau pakai DIPA Indonesia itu. Kalau menunda-nunda itu pemerintah Indonesia agak susah. Ya, Pak.
Tapi itu memang breakthrough, terus teknologi yang sangat selamat, ya kayak karburator sama injeksi. Nah,
ini ada perencana utama baru nih Pak Budi Kaliwanto ini, tinggal nunggu pelantikan ya Pak Budi ya.
Iya Pak.
Oh, ini syukuran ini.
Selamat Pak Budi.
Iya terima kasih.
70 tahun.
Iya.
Umur Pak 65 Pak.
Polisi papernya aja tentang PLTN ini.
Iya. Baru belajar itu Pak.
Kok baru belajar.
Makanya Pak Budi Kaliwanto ikut terus nih besok karem, ya kan?
Iya.
Ya.
Ya.
Nanti ada smart. Smart itu menarik karena Arab Saudi kan mau menggunakan smart kan. Ini ya, saya baru komunikasi dengan pihak Korea. Apalagi kalau nanti Nuklir kan sudah mendapatkan dari izin kan, ya itu luar biasa. Jadi masyarakat tahu situasinya itu. Nah nanti kalau penyukatorium juga kita berikan suatu kesempatan untuk memberikan presentasi dari kawan-kawan. Saya kira menarik. Dan kalau bisa kita mendapatkan speaker yang memang benar-benar dari pihak aslinya. Kalau kenapa kita mengundang Tsinghua University, desainer utamanya sebenarnya dari Tsinghua University. Jadi kemudian baru dipindah ke pihak vendors-nya. Dan sekaligus itu untuk menjawab HTGR yang 10 MW itu masih beroperasi karena di sebagian teman-teman di kita menganggap setelah komersial hidup maka itu akan dimatikan. Sebagai bagian laboratorium masih hidup. Saya kira menjelang maghrib saya harus akhiri. Terima kasih. Mohon maaf jika ada kesalahan. Sampai ketemu lagi minggu depan. Dan Selasa pun masih ada, yaitu webinar terkait menjelang conference.
Ada yang senasib saya itu sedang nyopir.
Oh iya. Kalau tertarik hari Selasa nanti ada webinar terkait masalah HTGR lagi, yaitu first webinar toward HTGR 2021. Ada pembicara dari IAEA dan juga pembicara dari Komisi Eropa. Itu moga-moga bisa berlangsung dengan baik. Terima kasih. Wabillahi taufiq wal hidayah. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.